So the first one is Cartesian velocity. You can actually also get the non-Cartesian or the angular velocity. Cartesian would mean the velocity in the x, y, and if you have a z, then z dot, right? So this is, so I'll illustrate this with theory, and then I will do some problem which illustrates how to use it. So theory. Yeah, so if P is a point and we found the position of the point in the global frame, so this is position of point P in frame 0. How do you get that? We've talked about how to do that using the homogeneous matrix. Q here is going to be the joint angles. Okay, so we can write that function because we've seen how to do that. Now what I'm going to do is I'm going to take the derivative, define the derivative of f df dq. So this is just from the previous slide where I talked about definition of Jacobian. Let's rearrange this. dq is, or rather df is j dq. Nothing stops me from adding a dt to both sides. But since I'm taking the derivative with respect to time, and time really doesn't appear in f, f is going to be a function of positions. This partial derivative is in fact the complete derivative. But what is df dt? It's basically the derivative of p, right? So dp0 dt, I got that from the expression that p0 is f of q. So I replace f with p0 equals j times q dot dq dt. Let me write it as it is, and then here let me put it as p dot 0 equals j q dot. So what sits in P for two-dimensional problems is something like x dot y dot, right? X dot, we write it as x dot p0, y dot p0. That's pretty much what P is. P is the position of point P, some abstract point. J is the Jacobian. And what is Q? Q, if you think of theta 1, theta 2, so on, to be the angle of the angles which P is a function of, then this will be theta 1 dot, theta 2 dot, so on. Right? In other words, what we have here is the velocity of any point P in global frame is the Jacobian times q dot, where this is the Cartesian velocity, and this is the angular velocity of the joints. Okay, so we can find the velocity of any point P using the Jacobian. It's just j times q dot. So let's see how to apply this to a double pendulum. So I'll draw a double pendulum and then find velocities of, let's say, the center of mass. So let's do an example. Let's skip to the example. we'll compute the velocity of center of mass of a double pendulum. That is two pendulums put together. We've looked at double pendulum before. I'm just going to redraw it slightly differently. I'm just going to draw it like I would draw a pendulum which is suspended from in the air. So fix an axis. Let's draw the two links. Link 1, link 2. Okay, let's this is my base frame, frame which is fixed to the world and will not move. Let's draw two coordinate frames. One is for the movement of the first link, so it'll be x1, y1, and then other one springs from the other joint, x2, y2. We can call this, well, this is the origin of frame 0, but it's also the origin of frame 1. This is the origin of frame. Is this notation? No. Let me use a different notation. This is O1 as well as O0, O2. Okay, let's specify the angles. Now I'm going to slightly, let me draw the angle this way, theta 1. So it's the angle made in the counterclockwise direction between the vertical downward direction and the first link. And then the second one, what you normally do is you extend the link 1 and you draw the angle between that extension and the second link in the counterclockwise direction is positive. Okay, so now that we have the pendulum, we fixed axis. Let's assume that the center of mass for the first link is here, G1. Center of mass for the second link is G2. And this distance, I'm going to assign, I will call that C1. And this one, C2. And I'll, of course, need the length of the first link. G1 and G1 and G2, the center of mass of the two pendulums. Okay, our goal here is to compute velocity of G1 in frame 0 and velocity of G2 in frame 0. Okay, that's our goal. And the way we'll achieve this goal is by computing using the Jacobian. So velocity of G1 is the Jacobian of G1 times Q dot, where Q dot is the rate of change of the independent variables. The independent variables are here theta 1 and theta 2. So it'll be theta 1 dot and theta 2 dot. Okay, similarly, velocity of G2 in frame 0 will be J G2 Q dot, and that would be J, it should be. Can you slow down? Okay. Okay, let me take a break. If you have any questions, let me know. Yeah, question. Yes, that is correct. it's the angular velocity. Some people like to call it omega 1 and omega 2. Okay, we assume that this is given to us. We just put that here. Okay, so in this formula, we can, are those q's or thetas? They are thetas. This is theta 1 and theta 2. There are no q's in this figure. Okay, I just take whatever is known. I know the angular velocity, which that's given to us. I don't know. I need to compute vg1, vg2. That's the unknown, and the only thing left which I need to compute is jg1 and jg2. Once I compute jg1, jg2, it's just a matter of subbing in the formula. So once we get the Jacobians, we are all set. Let's compute the Jacobian. Okay. So in order to compute the Jacobian of g1, what we need to do is we need to identify what the f is. So d, it's, remember, it's df dq. I'll just call that fg1. So what's fg1? It's basically the position of g1. So let me use the notation g1 frame 0 dq. Okay, all I need is a position of g1 in frame 0. Okay, so I'm going to write the formula for g using the homogeneous matrix notation. So g1 in frame 0 is h10 g1 in frame 1. Okay, so if that's confusing, let me just get that figure here. Okay, so that's basically falls from the homogeneous matrix derivation. There's nothing new there. Okay, let's try to write what g1 in frame 1 is and h1 in frame 0 is. So h1 in frame 0 is cosine of the angle. Now this is the angle made with the positive x-axis. So this is the positive x-axis. This is x1. I need the angle between x0 and x1. Okay, so you can go this way, but I would recommend that you always go counterclockwise because the convention is counterclockwise positive. So this is the angle which we're interested in. It's theta1 is given to us. I just put it from here. So in order to get the angle from x0 all the way to x1, that's going to be what, 270 degrees plus theta1, right? 90, 90, and 90. So that's 270, and then the theta 1. So cosine of 270 degrees plus theta 1 minus sine 270 plus degrees plus theta 1 sine 270 degrees plus theta 1 cosine 270 degrees plus theta 1. 0, 0. Okay, so that is this whole thing, what I wrote down, this matrix is R10. Okay, I also need to write the position of frame 1 with respect to 0. Right? What is that? That's basically this point. And you can see that point is fixed at the origin. So that the coordinate of that would be 0, 0, and then this 1 is the placeholder. Okay, so that gives us H1, and then G1 in frame 1. So that is, this is G1. If I want to compute G1 in frame 1, I want to look at the coordinate of G1 in this frame 1. Frame 1 is x1, y1. You can see that G1 is along x1, and so its coordinate is going to be C1 along x1 axis and 0 along the y-axis because it's along the x1 axis. So G1 would be C1, 0, 1. So this is distance along x1. This is distance along y1. Okay, what remains now is some math, and I'll just do that quickly. I'll just write G1 by putting these two values, which I wrote down here, and then simplifying the expression for G1 in frame 0. So G1 in frame 0 is as follows: sine theta 1 cosine theta 1 minus cosine theta 1 sine theta 1 0, 0, 0, 0, 1 C1, 0, 1. If you multiply this, you get C1 sine theta 1 C1 cosine theta 1 with a negative sign and then 1. So remember that this part, the first two lines, is actually the small g 1 in frame 0, right? It usually comes with that extra 1 added to it, that's just to make the homogeneous matrix work. But that's G1. So G1, 0 is C1 sine theta 1 minus C1 cosine theta 1. Q is theta 1, theta 2. And I'm interested in G1, which is TG10 TQ. So this would be, just to make it more clear, let me write this as XG10, YG10, and Q is as it is. This will be DXG10 T theta 1 T theta 2 DYG1 T theta 1 DYG1 T theta 2. So because G is a vector of 2 elements and Q is 2, the J is going to be 2 cross 2. Okay, so all that remains is to do the calculations now. So derivative of C1 sine theta 1 with respect to theta 1 is C1 cosine theta 1. Derivative of xg1, which is this quantity, with respect to theta 2. Since xg1 is only a function of theta 1, this will be 0. Okay, that's the first row. For the second row, I take yg1 and take its derivative with respect to theta 1. Derivative of cosine is sine, and then the negative sign. So cosine is negative sign, so plus, and then derivative of yg1 with respect to theta 2. So derivative of this with respect to theta 2 is 0. You write C1 not looking like G's. Okay. This one maybe. Okay, so to complete the final step, VG1, which is JG1, theta 1 dot, theta 2 dot, we have VG1. So taking this, multiplying it, theta 1 dot, theta 2 dot will give us C1 cosine theta 1 dot, C1 sine theta 1 dot.
JD1, was that C1 cosine theta 1? That one. All right.
Even this one?
The one above.
This one?
Yeah, this is
Sine and
those are separate. Okay. Put it together.
Cosine theta 1 C1 sine theta 1. So now they are together here. C1. Yeah, let me put the dimensions. So this is 2 cross 2. This is 2 cross 1. Okay, so what I'll do is I want you to try out and compute velocity of G2. I gave you the formula in here. What is that? Okay, the formula is here. You need to compute JG2. For that, you'll need to compute the position of point G2. I'll give you the final answer, but you expected to know this because I taught you how to do the homogeneous transformation. Okay? So let me write down the final answer and try to check what you get with my answer. So this is what I get. Okay, velocity of G2 in frame 0 is C2 cosine theta 1 plus theta 2 plus L cosine theta 1 C2 sine theta 1 plus theta 2 plus L sine theta 1 C2 cosine theta 1 plus theta 2 C2 sine theta 1 plus theta 2. I need some space. Then this will be times theta 1 dot theta 2 dot. And then this is a 2 by 2 matrix. 2 cross 2, and this is 2 cross 1. So when you multiply them together, you get 2 cross 1, which is what velocity of G2 will be. This is in frame 0. H10, why was it needed? Why was H1 needed? Yes, sure. So if you go, so here is, I've computed H1 0 with H1 with respect to frame 0. This is H1 0, and this is G1 1. So I just did not write it again, but it's needed here.